we propose a decoupled training framework for local feature extraction, which is named PoSFeat. Our framework is based on the describe then detect pipeline and use the camera pose as weak supervision to overcome the obstacle of training data collection. However, the simple combination of the pipeline and weak supervision can cause some problems, such as the false detection of key points. In this paper, we argue that the problems are caused by the ambiguity of weak supervision in joint training. When only one component is failed, the weak supervision cannot distinguish it, and thus, these components cannot be optimized correctly with the joint training framework. To address the problems, we propose a decoupled training framework. Different from the joint training framework, we decouple the training of description aid and detection aid. And because the robust key point detection relies on the descriptors, we first train the description aid individually. When the description aid is well optimized, we train the detection aid with a frozen description aid. In this way, the ambiguity is avoided. For the description aid training, we follow caps to compute the distance between the correspondence point yi hat and the epipolar line lxi as the objective function. And we propose a line-to-window search strategy to localize the correspondence point yi hat. This strategy makes full use of the camera pose information to guide the description aid optimization. Firstly, for a query point xi belonging to the image 1, we sample descriptors along the epipolar line in image 2 and compute the match distribution with the sample descriptors. Then we select the point with the maximum probability as a proposal. To avoid conversion to trivial solution, we add a noise to the proposal so that the local patch center will deviate from the epipolar line. Finally, we crop a local patch according to yi center, compute the match distribution in the local patch, and get the correspondence point yi hat. For detection aid training, we follow the formulation in disk and use policy gradient to achieve optimization. Note that since our description aid is well optimized, the match distribution PM of xi, is reliable. Therefore, the detection aid converges fast. We test our PoSFeat on 3 different datasets. On edge patches, compared with fully supervised methods, our PoSFeat achieves comparable results on illumination change and performs better on viewpoint change. And our method significantly outperforms previous weakly supervised methods, especially on viewpoint change. That is because the line-to-window strategy makes full use of camera pose information. On Action Day Night, our method outperforms all of the local feature methods and is even better than the metro methods. On ETH local feature benchmark, our model also achieves comparable results with previous works. The ablation study shows the effectiveness of the proposed contributions, and we should notice that the improvement of quantitative performance mainly comes from the better descriptors, as shown in the comparison between models 5 to 8. Our code are open sourced on GitHub. For more details and results, please refer to our paper. Thanks for your listening.